we will see what kind of difficulties generally we face in during testing and how to resolve that. So the first one is so I will thank Naveen, Pallavi, Shariyu, S. Krishna for providing the material. And at the last, I will also give a glimpse of my testing experience. So whenever you plan a testing, so what you should do? So first you need to do prototype planning. So it is like that once you have completed your whole circuit designing and you have got your fabricated IC, and now you want to test it. So now after doing this much effort, the IC become very dear to you. Want it to be work. It should work. This is what you wanted at the last. So but without proper foresight and test planning, it may happen that the IC is working inside, but you are not able to take signal out. Okay, just because of the testing methodology is not correct. Okay, so let's discuss some experience. So first experience is of a high-speed on-chip interconnect. So here you can see that there is interconnect and one transmitter and receiver. So it is a transmitter and receiver IC inside one. So what kind of different blocks inside it? Let's see first. So first is on-chip VCO for generating the clock. Okay, this one. So in that bias voltage of VCO is a sensitive DC input, and output of VCO you need to divide, and then you can brought out of a pin. Okay, so generally the VCO frequency is quite high, and taking out the high frequency is not a good idea. So you divide it inside the IC using a frequency divider and take low frequency output out of the chip. And transmitter and receiver circuits have some programmability digital inputs. Okay, so you need to actually sometimes turn on and turn off some of the blocks which are inside the IC. So for that you need to have digital input. Apart from that, there are some digital some of the blocks are digitally controlled, so you need to have digital inputs for that. Receiver has some control status indicator, digital output, analog voltage outputs, and receiver has high speed comparators, the offset of which needs to be compensated before testing the link. Okay, so differential DC offset compensation inputs, those are also present. Okay, so actually I am telling the experience of testing, but for any such kind of testing you need to do these kind of things. Okay, so high frequency analog buffers for measuring eye diagram at certain point of interest. Okay, so eye diagram also we have seen yesterday. So we know that for measuring the high speed signals we need to look into the eye diagram also. So you need to provide a provision for testing that also. And bias current inputs for op-amp, analog current inputs. Okay, so this is also some pins will have this kind of bias current op-amps. Okay, apart from that, the chip works at a voltage of 1.2 volt, and but so this is very low voltage as compared to all the ICs those are available in the market. So generally we use 3.3 volt. Maybe you have seen some of the ICs during your lab experiments for UG. For those ICs we apply 3.3 volt or 5 volt. But generally when you design an integrated IC, so it is in the range of 1 volt. Okay, the test includes a functional test and well as well as at speed test. Okay, so it is high speed circuits that we are talking about, so speed test is anyway there. But apart from that, we need to also check functional test. So sometimes what we do is we check it in low frequency, and then we increase the speed of the circuit and check whether it is working or not for high speed also. So the high frequency IOs, so this is also one important point, because what will happen that whenever ESD is the important thing, so electrostatic discharge. So whenever you it is always recommended that you should not touch the IC, otherwise the pad may get damaged because of the high current flow, because of a high charge transfer. So what you need to do is, but in high frequency input output pins and pads, generally we don't put ESD protection, because what will happen that whenever you put ESD protection circuit, it will have high capacitive load, so you don't want to load your high frequency IOs. In order to measure power consumption, different circuits have dedicated VDD input. So what will happen that if some of the blocks of the IC is consuming more power, then what you will do is you don't want to mix it with other all the blocks. Okay, so suppose your whole system is taking 10 milliampere current, and in that one block itself is taking 4 or 5 milliampere current, then it is a better idea that you give separate VDD to that block and keep 6 milliampere for all other, and give 4 milliampere for single block. So this is also a good idea to during testing. And in short, the chip has digital IOs working at 100 megahertz sensitive analog broadband RF pins and multiple VDD grounds. So till here I have talked about what kinds of pin we need. So in summarize, it is analog inputs, broadband RF pins, and multiple VDD and ground pins. Okay, so so this is one testing experience, but this is generally happens for all the system. But now I have talked about all kinds of pin available in the IC, so it is mixing of all kind of thing, DC, AC, RF, all those things. So so how to test this, because now it looks very quite difficult to test, because there are so many problems that may come because of different kind of properties of the pins. So to take care of that, you need to systematic plan the things. So first thing is, how do we plan the test of such a system? So first, get a list of the input output pins, decide on package accordingly. For this, one need to also consider the total power consumption of the chip. So generally what will happen that you need to there are different kinds of packages available, and you actually need to pick the package, so that you should have and when you are deciding your package, you should take care of the power consumption. And suppose your package, let's assume that it has 100 pins. So and your let's assume your whatever IC you want to test, it has 95 pins, let's assume. So you should always think like that this 100 pins package will not be sufficient for you, because you it is like that you whenever you apply going to apply VDD and ground, you need to give VDD and ground in multiple locations. It is not like that you will only apply VDD at one side and that is enough. It is not going to happen. Wherever in every distance, after some distance, you need to keep VDD and ground, so that the current distribution inside the IC will remain the constant. Okay, so that is why if your IC requires 95 pins, you should always calculate how many VDD ground will be sufficient to to handle this high current consumption, and based on that you should put sufficient number of VDD and ground. That is the reason why you need to actually pick your package wisely. So it is important to include the package parasitics while simulating the full circuit. Okay, so first when you have decided the package, you also re-verify it using simulation, because there will be some capacitances associated with the packages. Okay, so when you will connect, so suppose this is your bare die IC and these are pads. So and this is your package. So you will, and these are the, let's assume it has legs. So you need to wire bond it from here to here to connect them. So this everything will increase the capacitive load. Okay, so you need to also simulate, because this is high speed input outputs we are talking about. So you need to actually simulate this high capacitive load also, the value, by keeping that value. After the pin number and package is decided, you should decide the pin placement before layout. Okay, always keep the RF pin in the center edges of the chip. This pin have the shortest bond wire and hence the least inductance. So here if this is your IC and there are multiple pins everywhere in your package, then the corner one will have longest bond wire as compared to the this one. Okay, so this one will have shortest path as compared to two. So it is always preferable that here you will keep high speed your high speed pins rather than this location, because this will be this will have some extra wire bond length. Okay, and that will enhance the inductance also if you will pick this. So it is better that you choose this one, so that there will be less inductance. And for bond wire inductance, a good rule of thumb is 1 nano Henry mm. Okay, so 1 nano Henry per millimeter. So this is a rule of thumb, and generally rather than using the equation which is also given here, it is better that you this approximation is quite good. You can follow that directly. So if possible, keep the RF and sensitive analog bias pins on opposite faces. Okay, so in your package, the RF should be, if the RF are in this side, RF pins are this side, then analog and bias pins you should keep in other side. So here you should keep analog, and here you can keep RF. Okay, so they should be well separated. And there is use GSSG pad for RF IOs. Okay, so it is ground, source ground. Okay, pad. So generally it is in this form because generally these RF signals are in differential form. So if those are in differential form, then this, so for assume that here you have V plus, then V minus, then you always give ground to shield it from other signals. So you will have ground here. So that is why it is called GSSG. Okay, so ground, source, ground. This will reduce coupling to adjacent signals. Similarly, use ground pad next to DC bias inputs. Okay, and even it is advisable to use ground pads next to DC bias input also for shielding. So this is the whatever we have discussed. This is the same thing in picture form. So here you can see that if you will pick this location, then here we have our IC. So here you can see this is the IC bare die, and there are pads here. If we zoom, so you can see these are the pads. These are the pads, and these are the gold wires. This all the lines represents gold wire, and it is called wire bonding. Okay, and here at the last, this is the package. This one is package, and this is the package pad. Okay, so this is 64 pin package. So here you can see, so you need to make a connection from package to the IC. So for that you need to make you need to do it using bond wire. Okay, and it is made up of gold in general. So now here you can see that if you keep RF signal at this side. Okay, so these are high frequency signals. So then it is preferable to use DC signals at this site. Okay, similarly you can pick two or three different locations and do this kind of exercise.
Sir, just a question here, sir.
Yes.
And you said, as you said, DC bias inputs and RF side. Uh, uh, in a real environment, are you identifying by the pin numbers, or are they the pad numbers, as you pointed out? How are they identified? Like, I mean, left, right, top, bottom, or
No, this I actually identified means I didn't understand. Could you please elaborate more?
yes, sir. Like you said, like on the RF side, on the DC bias input side, when the testing is done, like are they identified by the pin numbers, or should we know the pin numbers? Like, on the RF side, the pin numbers are like 1 through 16. So that identifies as the RF side. And the DC bias inputs, are they from pin numbers 48 through 38, 33 through
Mm,
48?
mm,
Is that fixed? Fixed.
okay, so here there is nothing called RF or DC bias input, something like that.
Okay.
Maybe
Okay.
in inside the pad also, in pad there it may, you can differentiate these kind of things based on the whether you are going to put ESD or not. But in package there is no different scenario in that case. Means it is like it is same kind of pins all around the your package, and you are just making a connection. And now
Okay.
you are saying that okay, this is where I will put RF signals, and the other side I will put only an DC signals.
Okay, sir. It's user dependent, is it, sir? So you're saying it's
Yeah,
user
so
dependent. Pin numbers
yeah,
would be identified by the user,
yeah, so
by the
it is,
request. Okay.
yeah, so it is totally custom made thing.
Okay.
uh,
Okay. So some other user can interchange the numbers as well. So that's what you're saying. Like, for example, they can have
yeah,
DC based inputs like from pin numbers 17 through 32, or the other way
yeah,
around. RF.
yeah,
Okay.
so
Okay.
sometimes you need to do that because
Okay.
it may possible that you have RF only four pins, so you will
Ah,
keep
yes.
it here. But
Exactly.
yeah, this you need to anyway need to use it. So then in that case what you will do is you will try to make it close and try to take it out in this fashion, something like this, so that your RF will remain at the middle, but all other will go something like this in PCB design.
Okay, sir. That is from purely a physical limitation perspective, sir. Like, RF should be like 5, 6, 7, 8, and right from a physical
Uh,
design perspective, right? From
in
access.
physical design perspective, only perspective is that because if you choose this one as a RF,
Ah,
then the this bond wire length will be higher. So it
yes.
is better that you will pick this one so that bond wire length will be minimum and inductance will be less for RF signals.
Okay, sir. So yeah,
So
the
yeah,
inductance. Yeah,
yeah. So less distortion will happen for high frequency signals.
definitely, sir. Thank you, sir.
Okay, so how do we plan to test such a system? Use separate ground plates for digital and analog section of the chips. Okay, so generally these analog blocks are quite sensitive to the noise, and digital blocks generally they switch quite frequently. So because of that, there are a lot of fluctuation in ground in digital side as compared to analog side. So it is better that you separate them, the ground pads also. Okay, so and in general when you do simulations it is not possible, because if you in simulations if you do that then it will show error. Okay, but you can keep separate label and all those different thing in during layout itself, and can take it out separately. Okay, but for LVS checking you need to combine them. And apart from that, inside the IC, you should put decoupling capacitors in bias inputs and supply inputs. So it is like wherever you have DC running in any line, so with ground you need to place some capacitors, okay, so that all the high frequency signal that will appear in DC will be grounded using this capacitor. Okay, so you should put plenty of those capacitor wherever you find a space, empty space, you should put that. Okay, and now the bias node should be decoupled to ground or VDD depending on which type of transistor. So it depends on also the whether if ground or VDD, whichever is closer, you can keep this decap based on the closeness of ground or VDD. Okay, and to reduce the substrate noise, the same substrate taps should be there. So in case of NVL or NVL contact or substrate contact for case of NMOS, that also you should put frequently. Okay, and you should also isolate all the analog and noisy blocks using guard rings. Okay, so sometimes double guard ring also used to very sensitive blocks, double, triple also. Okay, and in during design of any transistor, so if you are designing a transistor, then single contact is not a good idea. Okay, suppose this is drain, this is source, this is gate, source, this is gate, then you should not only place single contact. There will be a huge reliability problem. Okay, always try to keep two contacts minimum. Okay, and to be in safe side, it is always you can if you can put, always try to put more contacts, more than two also, three will be a better choice. Okay, so this is for reliability issue, and apart from that there is some current carrying handling capacity of these contacts. So if a large current is flowing from this MOSFET, so you should also check whether what is the current carrying handling capacity of the contact, and based on that you should also pick the number of vias or contact. Okay, and so current mirrors are very sensitive block, so you always keep during the layout, you should always make current mirrors very in a very good shape, and matching, all the matching should be taken care of. Okay, there will be a mismatch in current, and that may result in not working means badly working IC. So in scale technologies where stress and strain is in channels are implemented for mobility enhancement, so transistors with multiple finger do not provide same current for all fingers. So so let's assume that I have a transistor of 10 by 1 micro. Okay, so if I divide this into, let's assume, 5 different fingers, each of the finger is 2 micro. So what I assume that the in each of the MOSFET, so here I have 5 transistor now, something like this. All gates are connected to each other. So let's assume drain is also connected, something like that. and gates are also connected, something like so. Earlier I had only one transistor. Now I designed five using five fingers, so each transistor is of 2 micro by 1 micro. Okay, so overall it is 10 micro by 1 micro. But in scale technology, the current density of this transistor is not uniform. It is higher at the middle, so it will go like this. The current density will go like this. It will not be constant. So what you assume that because I divided into 5, so in each of the fingers the same amount of current should flow. So let's assume here uh, 10 milli is flowing, so I will assume that 2 milli will flow in each of the transistor, but that will not happen. Maybe the middle one will see less amount of current, maybe 1.8 milli itself. Okay, and the corner one will see 2 milli, or other way around. So you need to always extract the transistor and check the how with the technology how it is behaving. Okay, so for digital assign keep registers in multiple operate this. So generally in digital designs you need to keep registers in multiple operate, so that in microcontroller it is easy to apply. Okay, and inside the IC you can keep extra bit unused. Okay, so it is only for when you are going to apply use microcontrollers or FPGA for applying control signal from outside. Okay, so serial to the chip can be done using SPI interface, which is easy to implement. So it is always better that you can go for serial interface. So less number of pins can be used of the IC. So again, place the components so that the traces are short and crossover are minimized. So it is always recommended that your traces should not unnecessary. You should not use long traces. Okay, so if you want to connect point A and B, so try to connect it like this only. So don't connect it like this or something by following the long traces. Okay, and also if any different block is there in between, then it is okay. Different block is there, then you should follow this path rather than this path. Okay, so if A, B, if block is there, then you should follow this path. Don't go like this. Okay, but if this block is not there and you want to connect A and B, so you should always connect directly like this. So a good PCB will be that your traces with high frequency signals do not radiate. Okay, and DC bias signals do not pick up noise. Okay, so that thing you should take care. And this electromagnetic radiations and pickups are duals of each other. Hence, the same rules apply to both DC and high traces. Okay. So these signals should always run over a ground plane, should be shielded on either side with ground traces. Okay, so generally all this signals, whether it is high frequency or DC, you always run a ground uh, beside it, ground line. Okay, to provide a shielding from the noise. Avoid sharp bends. Bends can cause current crowding and radiation. So wherever you have, you need to go like this. Okay. So let's assume there is one block here and you want to connect A and B. So then definitely you need to go like this. Like this. Okay. But this edge, this particular edge, you should always remember that you should not keep it 90 degree turn. Okay, always provide some extra contact here, something like this. So it the correct way would be that you will go like this and provide some angle here. something like this. So it is like this and this. Okay, so this should be like this, not a sharp turn. So this is not the right way, this is the right way. If signals must cross each other, they should cross orthogonally. Avoid long parallel runs. Okay, so this is the same thing. So uh, unnecessary long parallel runs you should not do. Okay, if one signal is going like this, and you want anyway in suppose you have started from here, and this is A, and let's assume this is B. If this is also running like this and you want to cross it somewhere, so if you know that you need to cross it, so cross it in initial level itself. Don't run in parallel long for a long distance and then do crossing. Okay, that is not a good idea.
Sir, one more, just a point here, sir. So in the avoiding sharp bends, how to, sir, is there a tool to identify that, like, to avoid sharp bends, and or like, I mean, if it's a 90-degree, for example, we might say it's a sharp bend. So is there a reference point, like, a reference tool which helps us to identify that?
In cadence, if it is in layout,
Yes.
in IC design, then it will provide error. But in
Oh,
PCB, you need to be careful during design. They will not provide the errors.
oh, okay. Is it just purely visual, sir?
It
Visual
is
reference?
purely visual in case of PCB. In
Oh,
case of layout design,
oh,
it will show DRC error.
okay, okay.
Okay, so however, this does not apply for RF traces. Strip lines for RF signal should never be crossed. RF signal levels in dielectric between the conductor and ground plane. Cutting the ground plane will cause reflection and radiation. Okay, so this is straightforward. So there is no. So you need to cut the ground sometimes, but you need to check, because what will happen that if you cut the ground, um, so it will cause reflection and radiation. So what you need to do is, you need to microstrip line should be shielded on both the side with ground signal. Place vias from top ground plane to bottom ground plane along the traces. So this is the rule in general, but actually uh, you should always, if any DRC file is available, then you should run the DRC. So plenty of vias should be used to stitch the top and bottom ground plane. This will reduce overall ground plane impedance. Okay, so it is like that. If you have ground, this is for PCB, and so generally we have bottom is totally ground. So and it is like maybe 3D picture I am not able to show, but this is, suppose this is your PCB, and so PCB will have a certain thickness, something like this. Okay, and there will be some metal lines that will running, and all your IC and other things will be at the top, and the bottom will be generally ground. Okay, so the bottom side you will have ground. So this is the bottom side, which is ground. So what so that ground will also run at the top layer. So you should always make number of vias to make a connection between ground and PC wherever you find. So you can make a circle here and make a connection with bottom here, make a connection with bottom, so something like this. Okay, so use multiple vias to make a good connection to reduce the ground impedance also. And while multi-layer PCBs are very good option, they are hard to debug and are more expensive. Okay, so more than 2 layer, it is very difficult to handle. Actually, it looks good, it looks compact, but and designing is also a little bit not trivial, and it is hard to debug and also expensive. If the design has multiple signal crossover, it is better to use two separate boards that mate with each other. Okay, so one such example is shown here. So rather than using single board, if you have multiple crossovers, you can use two boards. So this emulates a multi-layer PCB while retaining the ease of debugging. It also allows the low-frequency PCB to be made on standard FR4 1.6 mm substrate, while the upper high frequency PCB can be made either on RT Duroid or 0.8 mm point. So what is the meaning of this sentence is that because we want supportive PCB board for RF signal. So if you are going for two-layer PCB, means two different PCB. There is a motherboard and daughter board. So you what you can do is you can isolate your daughter board in such a way that it will only handle the RF signals. Okay, so if you are designing this board for RF signal, then what you can do is you can actually choose a material of PCB which is better for RF signal. So there are RT Durite or Roser materials available in the market whose dielectric constant is better as compared to FR4. Okay, so FR4 you can use for DC, and better PCB material you can use for AC signals, and you can keep it in mother and daughter board format. So this is the zoomed version, okay, of the same thing. So this is one such example of good PCB design, where you can see that a clean these are the ground vias. You can see that multiple places. Oh, this is slotting, this is ground vias. So in many places you will see that. Okay. Similarly, here also you can see one. This is RF signal. Okay, so proper PCB designing is done, and this is also one. This is completely for RF. For DC, here you can see the pin, and everywhere you will see transmission line. It is for RF and differential kind of thing. Okay, and this is the DC signal again, and these are the RF signals. These are the RF signal, then DC signal. These all are RF signals. So in case you have only few signal crossover, splitting the PCBs might not a good idea. Okay, so even if we have said that you should use mother and daughter board, but if you have only few crossover, then you should not go for mother and daughter board. It is better that if you use only single board, and for doing that, there are for RF signal also there are components available that is called RF crossovers, and even RF DC crossovers. Those are available in the market. You can choose them. Okay, these components are essentially surface mount 3D components that locally emulate a multi-layer PCB in an electromagnetically safe way. Okay, so these are the company names that provides such components, so you can use it and use a single board also. Okay, if you have few RF signals and crossovers. So for electrically short traces, the ground plane below a trace loads the trace capacitively. Okay, so this is, I think, straightforward. And for high frequency electrically short traces, you can opt to cut the ground plane below the signal to reduce the capacitive loading. Okay, so because the traces will be capacitive. For RF signal, what you can do is you can remove the ground below the RF signal, so that your capacitive loading can be reduced. Okay, so it is like RF is flowing and there is below there is a ground, then there will be extra capacitive load. You can remove that, but you need to do it very carefully, because what will happen that then the radiating it will start radiating. So what you can do is you need to actually perform EM simulations uh, and all those to actually know what will be the implication of doing so. Okay. So most wideband op-amps recommend these ground plane cuts. Okay, but you should do simulations to verify whether it is good for your particular IC or not. So and also vias, whatever you use, there will be some series inductance. Okay, so use multiple vias when switching planes from low inductance track like power supply, bias voltage or current, etc. Okay, so single vias is not going to work. You need to always use multiple vias in case of VDD and ground specifically. And this is the formula for inductance. And for 0.4 mm via in a 1.6 mm FR4 substrate, the value is about 1.2 nanohenry. Okay, but you can follow the rule of thumb that is we have already mentioned in earlier slide. So most mixed signal circuits need configuration settings which may be static or dynamic. Okay. For setting up such test, one can use microcontroller which has the test routine program in it. Okay, so this is common practice to use microcontroller and FPGA to provide testing signals. However, if your test routine in is more complex and involves a lot of data and processing, it might be easier to do using computer. So what you can do is you can collect the data and process it in computer itself. Okay. So we can interface a computer to a test microcontroller or FPGA to coordinate the entire test routine and log the data processed. Okay. So when if it looks quite simple that you apply microcontroller and apply signal from that, what problems can be anticipated in such test signal? So these are the problem. This is the problem. So there is ground noise of a PC. Okay, and you can see here it may be significant. So optical isolation, let's see. So ground of a PC can be very noisy and hamper our measurement. So in order to interface a computer, one should carefully isolate the ground of the PC from the ground of the test setup. Okay, so this is very important thing, and generally people miss it. Okay, and this is best done using optical isolators, also known as optocouplers. So similar components called digital isolators are also available, which couple using RF signals rather than optical. Okay, so either you can use digital isolator or optical isolator to isolate that noise. The test routines in the computers can be written in Python, and which is very easy to use, powerful programming language suitable for scientific computing. Okay, so this is user's choice. You can choose different language also, but Python is good. So for ESD care during your PC handling of PCB and ICs, you should always keep ESD strap with you. Okay, you should always wear it, and you should when you are wearing ESD strap, you should make sure that your table should properly grounded. Okay, it is not like that you have wore the ESD strap, but your ESD mat is not grounded, then there is no meaning. So wooden tables have different impedance depending on their moisture content. Use an ESD mat which is connected to ground on your workbench. Okay. And soldering iron should also be proper. It should be ESD safe. Okay, otherwise your IC will get damaged during the soldering itself. Soldering of PCB itself, the IC may get damaged. So if you are using normal soldering iron, then your ground tip you should need to ground. Here you can see the tip is grounded using a wire. Okay. And earthing a power panel is good. Otherwise, you will do is to end up stripping to a floating node. Okay, so if there is a disconnection this earthing, then even if you make all the arrangements that is mentioned just now, it will end up like a floating node itself. So over voltage care. So once you solder the test set chip, if you are testing the PCB for continuity, be aware of compliance voltages. Okay, so you cannot say, directly use multimeter on the PC board. Always check what are the voltage it can provide. What are the, even you should also check the switching voltages. Sometimes what will, even if the device provide 1 volt, but it is a bad quality multimeter or something, it will switch a high voltage first, then it will settle to that voltage. Okay, so that also you should take care. And so this is that you should take during the PCB testing and IC hand. So let's move to the second case, uh, case of digital PLL IC. Okay, in digital PLL IC testing, generally for any PLL IC testing, there will be two blocks. Where is one analog block and digital block. Okay, so particular in this case, these are the specification, but let's assume that we will just identify them as a low frequency and high frequency signals. Okay, because we are talking about testing. So this is the paired arrangement. So this is the IC, this is the PLL IC, and this is PCB traces. Okay, and we want to we have made a connection between pads and PCB traces. So generally it is a general belief that the IC should have pad at the corner itself. Okay, at all the corners the IC should have pads, and then only the packaging can be done and make a connection between IC and package. So it is preferable, but it is not always true. Okay, so anywhere in the IC you can keep pad, and you can make a wire bonding and make a connection. Okay, so here you can see that in particularly here the testing is done for this block itself. There are various other blocks also. Here also there is a block, here also there is a block, there, here also, but because we want to test only this block, so the pads were put at the corner of this block itself, and all the connections was made to the PCB using wire bonding like this. Okay, so paired arrangement should be such that there should be no bond wire obstruction to incoming RF probe tips, and paired spacing should be as per the bond to bond spacing allowed by the packaging companies. Like so this during the design of the IC, so beforehand you should know that from where you are going to do packaging. So what will happen that suppose you have put the your pads here and here, so there is certain minimum distance between each of the pads that can be that can be used for bond wire. Okay, something like this, that bond wire can be done. So there is certain capability of the companies that you cannot do less than that, otherwise they will not be able to bond wire it. Okay, so before doing the IC fabrication, you should know this kind of things. Otherwise what will happen that you will keep it much closer, and then the company will say that they will not be able to do bond wire, so whole money and IC fabrication get wasted. Okay, high frequency signal pads should be placed on the periphery to reduce the bond wire length and thus the associated inductance. Okay, so this is the same thing again. Your RF should be at this side, all the DC should be on other side. So this is what and this we have already discussed that this we do. So here we are, earlier we have talked about the PCB testing. Here we are actually talking about the probe station plus PCB testing. Okay, so all the DC signals we are going to apply using PCB board, but the RF signal we will directly apply using the probe station. Okay, using probe tips. So this is the wire bonded PCB. You can see. So this is the IC. So generally the IC is so tiny that it is very difficult to identify where it is. So here it is, and all these are decap. Okay, and these are RF or DC signals. So this is RF signals. Okay.
Sir, could you zoom out, sir? Don't mind if you can zoom out, sir.
I think this much maximum, but zoomed
Thank you.
version is already present here. So
Oh, okay.
this is the zoomed version of it. Okay, so this is the zoomed version. So here you can see that there is wire bonding. So it is the IC is here, and this is the wire bonding with the traces. Okay, so but it is so small that so you should know that what is the capability of PCB designer, so that you can keep these traces very close. Okay, it cannot you cannot keep it arbitrary. You should know the capability of the PCB designer, so that you can keep it close. Also you should know the capability of this wire bonder companies, so that they will be able to, you will place the pads based on the their capabilities, so that they will be able to wire bond it, and then you can able to test it. Okay, and this is the actual IC. So these are the pads. Here you can see this is the IC which is inside it, and this is the pads, and from this pad there is wire bond from here and here, and this is the overall PCB board. Okay, now this is the probe station setup. So as I have told you that the RF signal, because this is testing, we want to see the how good our PLL is working. So these are the these are the you can say that high frequency signals, but by PCB we are applying, and there are certain DC signals also. Yeah, these are the DC signals, and this is RF, I guess. This also looks like DC. Okay, so maybe in this particular board all the RF signals are taken and given uh, by the this ports only. Okay, so this is probe station, and this is the board that is used for applying the signals from outside. Okay, so these are the board, and this is applied from applied and applied in these pins. Okay, so now moving to ESD cell. So diode connected transistor either gets shorted or open, so excessive current drawn by the VDD. Okay, so if ESD breakdown has happened, then you can actually see it. Okay, so your that diode connected transistor either gets short or open. Okay, so you don't know it. So whenever there is a ESD breakdown, you can't say that the high amount of current will flow. Okay, sometimes what will happen, that a high amount of current will, sometimes no current will flow. So external ESD IC is placed on VCB for digital logic up to 100 megahertz. Okay, so you should always use some different ESD protection circuit also. So ground probe, tip, wire, chuck, pattern, even metallic end of tweezer before placing connection to the die. Okay, so it is extremely important that you will ground everything before handling to IC. So suppose you are using a wire or any, even tweezer to holding the IC. So everything you should first do ground, and then do. Even that is the reason why that even you hand your cloth also you should first ground and then go close to your IC. Okay, now there is one component that is called ferrite bit. So digital analog supply isolation. So maybe ferrite bit you all have seen it, but you have I don't know whether you have noticed it or not. But in your chargers, you must have seen that there is some close to in your wire there is a one circle. You can what cylinder kind of architecture. Sometimes you will find just in your chargers. Okay, in between the charger wire itself,
Yeah,
you will
this
see
is
some.
something like this. If you can see my camera.
Yeah, this is ferrite bit.
So this is the charger tip, and here at the end.
Okay, so so these are inductors. So these are inductors. So for DC you can use it. Okay, sometimes, but when you are using ferrite bit, then uh, what you should be taken care of that there will be certain inductance and capacitance associated with this ferrite bit. Okay, okay, because these are inductors basically, but generally nothing we can say that it is nothing called practical inductor or real inductor. So it is like a sorry it is like a practical inductor, not like a real inductor. So there will be certain capacitance and resistance associated with it. Okay, even because it is inductor, there will be certain resonance frequency of inductor. Okay, so when you are picking your ferrite bit, that should be properly chosen. Okay, so that this resonant problem of power distribution filtering network by lowering the effective Q of the circuit. Okay, so you can use it, but you should use it properly by looking into its specification. Okay, so and generally this is placed with VDD and gauge. That is why the in chargers, because it is kind of DC that you are going to apply, so this ferrite bit is placed in between in series. Okay, so this is inductor, so it will not pass AC signals. So there is another term that is called decoupling capacitor that you always put. So you always, whenever you put decoupling capacitor, you should always look into effective series inductor and effective series resistor to reduce the ripple voltage. And so series resonance frequency of choosing of capacitor should be 5 times greater than the system clock frequency. It is something like that your capacitor should not start resonating. Okay, so at least you should, whatever your operating frequency, the capacitor you are going to put should have 5 times more resonant frequency. Now this is some miscellaneous. Most of them we have already covered, but if it is repetitive, then also please bear with us. So DC current bias, bypass capacitor and series inductors are also used for DC current bias for decoupling noise. Okay. So component capacitor with a smaller footprint is chosen to minimize ESL, and match terminal resistor selected based on maximum operating current specification. Okay. So vias, large diameter vias preferred for reduced inductance and resistance. Okay, so earlier we have said that more number of vias should be used, but apart from that, you should also try to use large vias. And use of vias minimizes the high frequency traces. So copper island between trace connected to ground for trace shielding. Okay. So as a 0.8 mm was chosen to reduce the mesh transmission line width. Okay, so it is specific to this particular design, but you can choose as per your design. So in this particular design for testability option, the GPIO block acting as a configurator interface should have both write and read back feature. Okay. SPI used for device configuration instead of UART for easy detection of configured failure due to timing violations. Asynchronous reset applied to the system except SPI for measuring settling time of DU from initial state. Okay, and multiple current biases added for independently controlling gain of different modules. Okay, so this all looks very easy, and you can say that very simple thing. But what will happen that during when you actually do the things, sometimes you forget to recall the minute thing, and later you regret that, okay, if this feature was there, then we would have done the better testing. Okay, so always take care of all these small things. So during the layout consideration, so have sufficient slack and digital logic. So because this particular PLL IC is combination of digital and analog, so that is why you should not always design digital logics in tight constraints. Suppose you want to design 2.5 gigahertz frequency, then you should not tightly design it for 2.5 gigahertz frequency. At least design it for 3 or 3.5 gigahertz, so that even if there is a variation, process variation, time variation, still your digital logic should work up to 2.5 gigahertz. Not only digital and analog grounds are separated, but the return path is also minimized at analog to digital and digital interface using differential logic and separate power supply of intermediate buffer stages. Okay, so shielding important signals like asynchronous reset from glitches due to crosstalk using ground shielding and buffer staggering, and weak pull-up used for input press connected to digital transistor gates. Okay, so these are already we have, most of them already we have covered. Okay, so this looks like repetitive. So ultimately you can see here that it is the measurement result, but we are more we want more testing methodology than the result. So let's moving to the another case, that is again the VCO testing of PLL. So here the agenda will be that testing method using bare die testing, wire bonded die on PCB testing. So earlier was the RF signal was also applied on PCB, but here the bare die will be the RF signals of bare die will be tested using the probes. So and also we will see how to test VCO mode and PLL mode, because generally what happened that in PLL we want to test VCO separately, and sometimes that looks difficult, because if the operation of the external connectivity may damage will affect the performance of PLL. So this is again the test chip. In this test you see that there are different blocks. This is PLL, this is another circuit, this is again VCO, this is different, this is different, and this is different. Okay, so here you can see that each module have their own pads, and each module you can test it separately. Okay, so this is the testing method using bare die. So DC RF signals are probed using DC RF probe tips. So this is probe station. Here you can see, and RF and DC both will be applied. Here you can see that this is the board, and IC is placed at the center, and these are the DC signals here. These are DC signals. This is RF probe tip. Okay, so RF is applied from this side, and all other are DC. Okay, so this is the result when so this is the comparison of experimental result of bare die and wire bonded die on PCB. So what is done is this here you can see that this is RF's probe, this is DC probe, this is DC probe, this is again RF probe. Okay, So here you can see that the same circuitry is tested using uh, probe tips. Okay, then this kind of center frequency came. Okay, now what they did is they designed a PCB. Okay, and did the wire bonding. Here you can see wire bonding was done, and RF signal they have used, they have tested using probe, but all the DC signal they have taken out using the PCB. Here you can see. Okay, these are used for DC testing, and RF they have tested using the probe. Okay, so probe they will apply from here, GSG, and all other signal they will apply from here, by here. So you can see that because of the second method, the wire bonded PCB measurement, here you can see that the 3 dB bandwidth has improved. Here it was 5 megahertz, here it is 6 kilohertz. Okay, so this is the center frequency. So the variation of 3 dB is now improved 6 kilohertz. Okay, so just by adding off-chip decoupling capacitor inductors on supply DC bias lines and using coaxial cable to supply DC signal. So what happened that because now your DC signal has improved because of all this decoupling inductors and all those things. Actually your performance looks better. Okay, so it is something like that your IC was working fine, just because of a bad method of testing here you are end up getting a worse waveform. So isolated your DC signals all properly, and then you have checked your again the same response, then it is better. Okay, so you can understand that how the testing is important. Proper testing is important.
Hello, sir. Hello.
Yes.
Sir, there is one doubt. It is from 6 megahertz to 5 kilohertz.
Yes.
So that much difference we will get.
Yeah, this is 3 dB
Bandwidth.
bandwidth
Okay. Thank you, sir.
from the center frequency. So earlier it was 5 mega, that is bad. Now it is less, 6 kilo. So center frequency should be proper.
Okay.
Okay, so now testing on chip VCO within a PLL loop. So here you can see that this is a loop. Okay, and now you want to test this VCO. So there is two mode. One is you want to test whole PLL, and another is only VCO. But you don't want to do separate isolated VCO to do the same. So if you have you want to test the VCO, so first thing what you need to do is you need to take the V control out using a pad. Okay, so this is first thing, and now this is whatever you have taken out, this kind of external circuitry you need to put, so that there should be a high resistance of switches when it is off. Otherwise what will happen that if this is on during the PLL operation, then your PLL will show a very bad result. Okay, because the PLL is very sensitive block to the variation of this V control. So to take care of this, you need to put this kind of circuitry where you will actually put a switches, and by turning it on and off you can actually apply it from outside. Okay, and during when it is not off, when this is not in operation, then the particular PLL will see very high impedance. Okay, so it is like if low off resistance switches are used, can inject noise on control voltage during PLL mode. Okay, so use low width large length transistor for switches to achieve high off resistance. So this is the again the but we are not that much interested in measurement result, but you can just look at the measurement of free running wide tuning range VCO suffer from large frequency drift due to small V control fluctuation due to large VCO gain. Okay, phase noise measurement not accurate. So now So now here you can see that now testing on chip VCO using off chip PLL components. So testing of high frequency VCO FD frequency shift can be observed as compared to simulated result. Off chip PLL component give the flexibility to vary the loop filter parameters charge pump current. Okay. So this is all the setup. So in PLL, generally on chip PLL is preferred, but sometimes what will happen that some of the blocks you keep off chip. So here the VCO is on chip, this much is on chip, and these are off chip. Okay, so to check whether in this VCO can be further improved or not, and sometimes many of the blocks are in your mobile or something, they keep it off chip intentionally also, so that you will get better performance as compared to on chip PL. Test setup for VCO FD using off chip PLL board. So here the same thing is shown. So here the evaluation kit is used of analog devices, and then the again wire bonded die is connected to the board, and then with a spectrum analyzer that is tested. But generally what happens that if your VCO is working at very high frequency, here it is working at 11.52 gigahertz. So what you do is you generally put many dividers inside it, and you divide it so that you get a relatively low frequency. Why we do that? Because generally the cost of the equipment are very high, so it is very easy to it is much cheaper that if you get a low frequency spectrum analyzer. But if you go for getting 3 giga spectrum analyzer, and the cost of 3 giga spectrum analyzer is much less as compared to if you go for 12.5 gigahertz. So maybe if this is of 20 lakhs, then this may be of 40 to 50 lakhs. So that is the reason why what you do is you will even if you have high frequency, you use divider and put it down to the low frequency and then test it. Okay, similarly with 60 giga, because 60 giga maybe spectrum analyzer may cost up to 80 lakhs. So it is better that you use divider inside it and then test it. Now the next case, that is PRB with VCO. So this is the circuit design and the layout of it. So here you can see that there are very different blocks, VCO, everything is inside this particular circuitry. So here you can see that everything is shown, like here so many, here it is VCO is here, then there is buffers, and buffers are here, and then coupling capacitors, and this is PR based generator that is here. Okay, so this is the particular IC, and in fabrication, after fabrication, you can see that this is the IC, and here also this particular IC is designed and in a provision of testing in such a way that you will keep all the DC signals at here you can see that all the DC signals are taken out to the PCB, and here AC signals can be applied from here. So maybe GSS probe can be used to apply from this side, and also GSSG probe can be used to apply from this side, and all the DC signals are taken out using wire bond, so that that can be applied externally from here. Okay, so this is a common practice during testing for bare die testing. Okay, all the precautions are already we have told that should be taken care of. So with this, I thank you all of you for listening this talk.
Sir, just a question, sir, here. Regarding that analyzer that you just talked about, sir, is it that 80 lakhs? Did you say that analyzer costs 80 lakhs, sir? there earlier.
Yes, sir. For 60 giga and more, it is close to 70 to 80 lakhs.
Okay, just the analyzer. Okay, sir.
Okay.
So the alternative to that one is what would be the alternative, sir?
In case of VCO, there is an alternative because you can divide the frequency.
Okay.
But in other cases, if there is no, sometimes you need to have that instrument.
Okay, sir. Okay.
If, based on the application. But for VCO, even if it is high frequency VCO, you can always divide the signal.
Okay.
So you don't need to rely on very high costly equipment. You can actually do testing using the low cost equipment.
Okay, sir. Okay. Thank you. Thank you, sir. Thank you.